My name's Fred Meyers. I work over at Western Cooling Efficiency Center. This is a continuation of some work we've been doing. If you came to Energy Bites last year for the virtual series, Curtis talked about sealing existing homes using our aerosol technique that was developed here and then commercialized. So this is continuation. I'll kind of do a quick overview in the first few slides and then go into what we did new just the last couple months. So why do we care about leaky houses? Well, in the US, the residential building sector accounts for 23% of all energy use, and 43% of that is space conditioning. And then 30% of that is just due to air infiltration or leakage. So 9.5 quads for space conditioning, that's a ridiculous amount of energy, a quadrillion BTUs. That's a pile of coal 10 feet high, 1 mile wide, and 3.3 miles long. In addition to the energy savings, there's newer codes, standards that are requiring tighter envelopes, like the International Energy Conservation Code and DOE Zero Net Energy ready homes are all 3 or 2 to 5 ACH 50. ACH 50 is air changes per hour through your space at 50 pascals in a house. So if it's like really, really windy outside, you can get to 50 pascals in your house. But these tests are typically done under pressure. 50 pascals is the standard. So what we need is a reliable method for consistently making tight envelopes without huge amounts of manual labor and materials costs. In addition to energy savings, there's health benefits. You can reduce cross-contamination in multifamily units. You can avoid breathing wildfire smoke. And you can then, if you have a tight envelope, you can take great advantage of heat recovery units or energy recovery units and advanced filtration techniques. So our technique that we've developed is aerosol sealing. So you pressurize the house with a blower door, which is, if you're not familiar, exactly what it sounds like. It's a frame you put in a doorway with a giant fan, and you pressurize the house. You pump in a bunch of liquid sealant combined with high pressure air, and it creates this fog, this mist in the whole building. And that will seal the house essentially. And these particles will accumulate along the edges of the leaks and then eventually create an airtight seal. So these are some small pictures. I don't know if you can see, but it will seal gaps up to like 3/4 of an inch. So last Energy Bites, Curtis was talking about this project specifically. From Department of Energy, Building America is the sponsor. And we've had a lot of success doing this in new homes, but we want to do this in existing homes. So what the challenges there are that you need to protect every single finished horizontal surface because this stuff gets everywhere. It's a sealant fog. It's very sticky and can disrupt the occupants. And we also want to do this and minimize the amount of mess, minimize the time it takes while still sealing the house. So occupant-friendly sealing is what we want. And like I said, aerosol sealing in occupied spaces requires covering surfaces and removing furniture. And we typically have been doing this in this project during renovations or when tenants are moving, so there's no personal belongings. So what we want is to do this without disturbing the occupants. And to do that, what we're going to do, or what we have done, is seal through the attic. So instead of pressurizing the house, we're depressurizing the house, and we put our setup in the attic, and we seal the ceiling. And this is, we're not going to seal every single hole in the house because now we're ignoring these kind of holes in the walls to the outside, but typically 51% of the total leakage is through the ceiling to occupied space. So it's still a great opportunity. The challenges here are we need to prevent significant amounts of aerosol from getting into the house. And the temperature and humidity in the attic can affect the performance of the sealant. And you do need to vacuum out your insulation. The attic insulation will create kind of a barrier, and the sealant will just settle on top of that instead of getting to the leaks themselves. So this case study, we went to somewhere in Central California and sealed some multifamily apartments, 750 to 1,000 square feet. They were already getting some energy upgrades and already had the attic insulation removed, so that was a great opportunity for us. So we sealed 3 units over there. Here's this picture again. We're depressurizing the house. And then you can see the blower door and us set up essentially in the living room. Nothing's covered. And then our nozzle sprayer is just sitting here in the attic, waiting for the test to start. So the sealing process, first we want to go through and make sure we're closing up huge leaks. If it's bigger than like ½ an inch, we're going to let a lot of sealant into the occupied space and maybe make a big mess or damage something. So we went through and with a can of the expanding foam and sealed up the big stuff. There wasn't much to do. It didn't take more than 20 minutes for us to go through and do that. We monitored the,
Can we ask questions?
Oh, yeah.
As you go?
Why not?
So where did you find the big ½ inch holes?
In the stove vent, the connection between the stove vent and the ceiling. Yeah, that was a big one.
How about light fixtures?
Light
I
fixtures
hear
are big.
they're a mess.
Yeah, I have a picture later on of us looking down at the top of one. It wasn't a huge seal, but we didn't have to seal it manually. Light fixtures, yeah, definitely. The electrician will definitely create a bigger hole than they really need to. But this graph we're looking at here, the yellow is the leakage airflow at 50 pascals, and x-axis is time. So this whole process took an hour. Blue is the sealing rate, so how much CFM reduction we're getting every single minute. So it's pretty much a derivative of the yellow line. Ignore the mess in the middle. I don't know, I think we're just messing with our equipment at that point. So you see that this kind of has an exponential decay. So you can keep doing this for 1 hour, 2 hours, 3 hours, but you do get diminishing returns and eventually it does level out. So we were able to get significant reduction in leakage. Here's some pictures. These next few slides are just pictures. Left is before, right is after. This is some Romex going through the ceiling. This is a picture in the attic looking down. You see the electrician was, this is pretty a typical hole. Sometimes they're just not careful, but you can see it's sealed up, airtight. This is a light fixture looking down, a can light, a newer one. They just upgraded to LEDs. You mostly see the hole up here on the top left. And then again, on the right, you see it all completely closed up. This is a wall cap, atop of a wall, and interfacing with some sheetrock. You see this line up here is just totally open to the downstairs. And then zoomed in and after our process, you see that completely closed up. During the sealing, there was some fog in the occupied space, but it wasn't a health concern. We were in there, it was fine, and there was no mess to clean up afterwards, and we didn't damage anything, so that was good. It's a big success. Our results for these 3 apartments was about 55% leakage reduction on average, which is huge for just how long it took and how easy the process was. At the same time we were doing this, there were a couple other contractors on site. One was sealing manually with a spray-on elastomer. That material is, they essentially get a paint sprayer, and instead of spraying paint in the attic, they're spraying an elastomer over holes that they find. And the other process they were doing is just canned expanding foam. They were crawling around the attic looking for stuff to seal up. So our process got about 55%. The spray-on elastomer, maybe 26, 25%. Canned foam, basically nothing. One of them actually increased leakage. We think that's just experimental error. We think there's just zero reduction there. So this was great case study. We were able to seal in the attic, and it was very effective. We didn't need to protect any surfaces or wait for tenants to move out. Setup was easy and it was fast. And this could be easily commercialized and bundled with like an attic retrofit package, because this, especially in older houses, attic insulation is not great. So you could buy this as a package and significantly reduce the leakage in your home. That's it. Any questions?
All right, any questions? And if you're online and have a question, please feel free to chat it or raise your hand and we'll get to you next.
Thank you. This was a great compact presentation. My question is that, can I have these slides? I will show them over in Finland to people who would be interested in this technology.
Yeah, absolutely.
Great.
Yeah. And maybe I'll get Curtis's slides from last year too.
Yeah, it's all on our website. I'm happy to, I can share the link.
All right. Very good. Thanks.
Yeah, I'm curious how the contractors that were on site while you were working responded, and if they were interested in the technology, or if they, just kind of have their response.
Yeah, we had the contractors there, as well as some representatives from the people who make this stuff. And they were all super interested, and they got connected and traded business cards. So hopefully this gets pushed along further quickly.
I'm also curious if you think this could be used by electricians or people who are installing stoves, or kind of these points where the leakages kind of occur, if you think they could use it to seal after their process is completed.
In general, it's pretty easy to do. There is a training process, because they've been doing this in new buildings for quite some time now. So there's a structured training process that the contractors get, and some nice equipment that they can buy. So it's pretty straightforward. I say electricians and contractors can learn and do that pretty easily.
We have a question online. So Dan is wondering, what is the expected cost of the aerosol versus other approaches? I know you guys have looked a little bit at that, but.
That's a good question. I don't have the exact number off the top of my head, but I will say that the manual methods are super labor intensive. It took them hours to do the elastomer stuff and a couple hours for the canned foam, and that's just a 1,000 square foot apartment. And we were done in a couple hours, and that's including all of the like extra little research pictures and data we were taking. So I think labor is the biggest cost there.
So to be determined, but are you guys looking into that? Like kind of
Yeah.
comparative? Okay. So stay tuned, Dan. And then Claire had a question about whether you can speak to aerosols and kind of, VOCs or health or climate concerns with the material that's being used.
That's a good question. The material itself is non-toxic and environmentally friendly. Ideally, when you're doing this when you're spraying in the house and there's that really dense fog I was talking about, you either don't go in or you wear a full face mask, respirator. There are some concerns there with respiratory, like you don't want to seal your lungs, right? But it's essentially a low VOC sealant, like silicone
Paint or
caulk.
something,
Yeah.
Any other questions in the room or via Zoom? Kelly's got one.
Yeah.
I think your 2 hours though was for an attic that already had the insulation removed.
That's correct. Yeah.
And that can be difficult or not difficult. Yeah, I think if it's rolled in fiberglass, it's maybe not that hard to unroll it, but otherwise, if you're vacuuming out loose fill or something, it would be nice.
Yeah, they did take a while to do that. But you would also have to do that for the manual methods as well.
Sure.
Yeah. Which is why combining it with a whole retrofit package is an opportunity.
So in new construction, is the preferred method to fog the inside rather than to go up in the attic and do this before they put insulation in?
Yeah, because then you're also getting the walls and the floor in addition to the ceiling surfaces. And it can get pretty low, like ACH1, at which point you have to install mechanical ventilation just to meet code.
But you got 50%.
Yeah,
right?
which
You
is
got
great.
50% just through the roof.
Yeah, and this was a slab foundation. If it's a raised foundation, there's probably more floor leaks. We want to try sealing under the house, crawl spaces, maybe. We'll try it.
You guys are approaching it from every angle.
Yeah.
Great, well, thank you.
Thanks. Great.
All right. Another cooling center presentation. Oh, wait, here's Miriam, she's gonna load you up here.
That's a very good analogy to explain what
Thanks.
Thinking.
It's a lot. It's quite a bit.
Oh, it's perfect. Is it up there? Oh, it's up there. I was looking at the computer screen. All right, Subhrajit.
And it should go ahead and let's make sure it. Does it change? No, it doesn't. Yeah. All right, let's do this then. We go ahead and close this. We'll close this.
Subhrajit is both an energy graduate group student and an employee at the cooling center, so he's doubly busy.
There we go.
Nice, thank you.
And
Here we go.
Okay, hi everyone. Today I'm going to talk about energy savings from a combined heat recovery ventilator and an indirect evaporative cooler. It's a lot of words for people who are not really familiar with the technology, but I'll step through it, I promise. Okay, so energy recovery in buildings. How do you do energy recovery in buildings, and especially with ventilation? It varies from I would say different climate zones, but in general, in winter you have cold outside air coming in, and it exchanges heat with warm stale air that is exhausted out of various activities in the house, and it exchanges heat and gets preheated before getting delivered into the house. So that's the whole idea. You just preheat the air, and you do it for free pretty much. And usually the reason it says preheated, you cannot get to the temperatures of the heating that you want. So it's like integrated or paired with a active heating device like a heat pump or a furnace or something that will, again, second step, heat it up to whatever temperature you want. Like if you want an 80-degree room, you would get there. In summer, it's hot outside, so like the warmer air that is coming out of the building is usually again used. But in this case, what I'm going to talk about is using indirect evaporative cooling to cool down on the side of on the exhaust side and cool the air, draw heat from the air that's coming in, the ventilation air coming in. And I'll talk about it like it is able to provide passive cooling. So in this case, we don't need a active device to cool it. It could provide passive cooling in a lot of climate zones. So that's the basic idea. The unit we are testing is, so HRV is heat recovery ventilator, which is what we are calling during the winter season. It recovers the heat. And in the summer, it's an indirect evaporative cooler, IEC, where it's cooling with some water in there on the right side, you can see. So step into this. So you have got outdoor air coming in, which is cold in winter. And it gets preheated by the warm stale air coming from the building. And it's then delivered into your into the rooms and conditioned space. In the summer, this hot and humid outside air comes in, and in this time you'll see that water is on the secondary side, or the indoor air side comes in, and it goes through and exchanges heat or draws heat out from the outdoor air and makes it cooler to be delivered into the conditioned space. The whole idea of indirect evaporative cooling is that you don't add any additional humidity. In like a lot of climate zones on the East Coast, we have got a lot of humidity. So indirect evaporative cooling doesn't add any humidity to the outdoor air, and it gets applied into the conditioned space. So
Sure, question, could you go back?
yeah,
So Subhrajit, when you said indirect cooling, I thought that you weren't adding water to the exhaust air, but that's not true. You're adding water to the exhaust air. You're making that much more humid, but because it's the exhaust air, it doesn't add humidity.
to the product air, your supply air.
Got it. So it's direct evaporative cooling on the exhaust air.
Right,
Got
so our main supply air doesn't get any humidity.
Yeah.
So that's the whole idea we go with. This is what the unit looks like to get a physical dimension of like, what it is like. It has got air coming, outdoor air coming in, and there's some channels it goes through, which I'll show in the next slide. And then the return air or the indoor air that comes in from the bottom. And there are a lot of terminologies used in literature, like, primary air, outdoor air, or product air, are all the air that we're talking about comes in from outside and is the ventilation air. And then secondary air, indoor air, or like return air is something that is getting exhausted. So excuse me if my terminology goes back and forth on that. Yeah, so this is the core of what it is inside the heat exchanger that I just talked about. You have the primary air, outdoor air coming in, going straight through, and you have the secondary air, that's like the exhaust air from the conditioned phase coming in. And this top part is dry, but in summer when it'll go through the hole, the secondary air, and to get wet and exchange heat with this number 2, or what I'm calling the heat exchanger surface, number 2 surface. And that's where the most of the heat is getting transferred. There's also some heat where, this is called an M cycle heat exchanger in literature, and they have used this methodology where the number 1 heat transfer surface also pre-cools the air before going through the holes. So these are the channels dimension. They're pretty tiny, and their whole idea is to in fluid flow, it's laminar flow that goes through inside, and there are all sorts of other geometries that we have to take in account, but this is just to give an idea. In the lab, we put it into, we have got outdoor chamber in the cooling center and an indoor chamber. In the outdoor chamber, we condition the air to whatever outdoor conditions we want to test it at. And that can vary, like, for winter, what do you want, and one for the summer, what do you want. On the indoor chamber side, we are interested in usually using this kind of setup for schools. So we looked into if there's a lot more students in the house, in the room, how does it increase the humidity? Everybody is breathing out some sort of humidity and different conditions. So we try to model that or test that part, and we looked at different humidities, which would be I'll be showing results on. We have a lot of instrumentation we use usually to measure the different humidity and temperatures and flow rate. The modes I talked about again is the winter mode and the summer mode, which is the HRV and the IEC modes. We tested balanced and unbalanced. So balanced is basically if you have the same amount of flow rate on both the exhaust side and the primary side. So basically the amount of air getting drawn out from the house and the amount of air getting into the house, ventilation is the same, but the pressure stays the same. It's like balanced. And unbalanced, you have a little bit more pressure, more air coming into the conditioned space. So you have got little higher pressure so that no contaminants can come in. So it's unbalanced flow rates.
Excuse me, can I
Sure.
ask like a maybe obvious question?
No, sure. go ahead.
So the chambers are separated by like metal, right? And there's like heat transfer through the metal?
Like you're
or-
talking about this part here?
Or like if you go to like the previous slide? Yeah, like you know how you have your like different channels, like those are like separated by metal, right? So the heat transfer is happening through the metal? Or like how are they separated? I guess.
Oh, it's like the material is like some sort of, I need to go back to it, like some sort of poly, it's not metal. It's like, it's difficult to make these things like such intricate details with metals.
Mhm.
So they will do some sort of, I would say, some paper polyurethane or something like that. So it's very flexible. in
Super
there.
thin.
Yeah, and they have got like fibers in there, so especially in this wet channel, there are fibers sticking out so that they can hold the water,
Got
like
it.
in indirect droplet.
Okay, thank you.
So coming toward the results, I think there is, in the winter mode or the HRV mode, we have got, we tested 3 different flow rates. And what I'm showing here is as the outdoor temperature increases, so this is winter, just keeping in mind. And you know, I'm trying to use SI units, but sometimes I do have to go back and forth. So our indoor temperature is 21 degrees, about 70 degrees Fahrenheit inside. And outside is cold. And as you like outside temperature drops, there's a lot more heat that can be transferred and you know preheat that you don't have to have any active heating done on. So if you're using a furnace or a heat pump or any type of heating device, you are saving this much energy from that device. That's what I'm calling the Q preheat. And the primary, so what I'm showing here is that the primary air temperature, so this air temperature is a significant impact, which is obvious because that's the temperature driving the Q. Higher flows have steeper change in Q. So as you can see with higher flow rates, as the temperature increases, there is a huge drop. There's the steeper drop. And for lower flow rates, the drops are not as visible. The other thing, as I would notice, and you'll notice it in the summer months, humidity has an impact there in summer, but not in winter. So it's mainly dependent on 2 variables, this outdoor air temperature and the flow rate. For the summer mode, it's a lot more busy data. The reason being is that it depends on 3 variables now. Now it depends on the flow rate, the temperature, outdoor temperature I try to characterize here, and also the indoor humidity that I talked about, like with our indoor humidity changes with number of people and heat and all that. So indoor humidity plays a role in summer months when we are trying to cool the place. And for this condition, we thought in summer, usually the room would be about 75 degrees Fahrenheit. And in this case, the Q, the heat transfer, the cooling that you could do, it increases as the outdoor air temperature increases. It also has depends on the flow, the more the flow, and we tested at various different flow rates, and it has an impact. Higher flows have higher cooling capacities. And finally, it also the humidity. The humidity has an impact too. So if you have a lower humidity, your cooling capacity is higher, and that's how indirect evaporative cooling works. If you have less number of people in the room and less humidity in the inside, or you're not cooking, if you're cooking stuff and adding humidity, obviously that has an impact on the indirect evaporative cooling portion. So this is all the testing that we have done, and one of the things that you can only do so much test. It requires so much effort. Like we have to wait for like the temperature outside to get there, and like it's very critical to have like both outdoor and indoor stabilized. So we wanted to have a model. So, and that's like for like characterization of this, so that you can use it in other conditions and see how that works. Like now that we have tested a few points. So the way we do this then like is heat transfer is like we just break up into different segments. Like I tried to model, like show it, like everything is like broken up, and you treat it as a single heat exchanger, and like try to model, like maybe you can assume that it's linear, everything is like easy to model. So that's what we've tried to do. And the working air is the room air coming in, indoor air coming in, and it goes through some sort of hose. This is the design pattern that the manufacturer has done. I don't get too much detail into it, but the main thing is that with the winter mode, we're able to predict things very closely, and that's because it's a lot simpler. It's just normal heat exchange, not much water in there, and we got pretty good at predicting the heat transfer and the energy savings. But interestingly, what I am going to show is the summer mode, where if the outside temperature is really high, we started seeing some deviation between our model and the experiment. So on bottom you can see it's the experiment, and this is a model, and this is when model, and this dotted line is when model and experiment line up. And we started seeing that, oh, like our experiment is showing more heat transfer, whereas our model is not predicting that. And the reason is that there is, with higher humidities, there is condensation that happens. So air comes in and it condenses out some of the moisture, and we are not taking that into account in our first phase of the model. This is what I would say, like the method we use, that you use the sensible heat and the latent and sensible coming on this side. But there is this portion, that extra condensate film, that builds up when there is high humidity on the outside air. So what do we do? So I added the condensation phenomenon to the model, and we got a good parity plot between model and experiment. So that's like one of the biggest accomplishment I think we had with modeling this really complex geometry, but also able to include condensation whenever you have high humidities outside. Oh, the other interesting thing that I thought would be interesting to showcase is, when can you do passive cooling? I mean, when I say passive cooling, is like cooling without any normal air conditioner, like with compressors and refrigerants, which is like usually has very high carbon footprint, and also high GWP refrigerants that come with it, where if we have to do just based on this device, where all and what are the conditions it can be done. So I modeled this with the passive cooling, as it depends a lot on the indoor conditions and outdoor conditions. So I modeled it based on if the indoor humidity is about for 75 degree Fahrenheit and 50% relative humidity, which is the AHRI test condition, the rating test condition. And I looked into different flow rates over here and different outdoor temperatures. And this is the supply temperature. So as long as we can supply anything below the existing temperature of the room, we can cool the place. So if the current room is at 75 degrees, 23.8 degrees Celsius, if we supply air at anything lower, it can do cooling. I mean, it might take a long time, but you want to be lower, but the idea will work. So, one of the things that this is what I thought would be cool to look at is it depends, for higher flow rates at about, I don't know, 37.5 or 38, we wouldn't be able to do any passive cooling. But at lower flow rates, we could do a lot more passive cooling And that's just how much area available you have and how much heat transfer is available to you. And the device can do the cooling without any active air conditioner in place. The future work, I would say, is to use this model. I use the model to create this. So use the model to look at different zones, like climate zones in the US or different parts of the world, to see how much energy savings you can get. Do you really need an active device for cooling? So, yeah. I want to thank the WCC team here, who we worked together to get this product tested and modeled. So, questions?
Thanks. Right, questions in the room, and then we'll go to Zoom. If you're on Zoom, feel free to put your question in the chat or raise your hand.
So I have a visual image of the size of this. What type of, how many square foot is that designed to handle?
Well, that's the thing. It depends. Like the cooling capacities and all that, design is very much based on outdoor conditions. So if you are in Davis or Northern California, you're very suitable for indirect evaporative cooler like this, because your outdoor conditions are pretty good for that kind of. The other, I mean,
But that's more than one house. Would you have that structure for one house in Davis?
yeah, I think it's, yeah, definitely. It's the top. So when CFM is 1300 CFM that the unit can deliver. So I don't know, Fred, what do you think, like square footage wise? I don't have direct idea of how much 1300 CFM will provide.
Subhrajit, let's say it was a house or something like that. Then would you also have, would the air there then feed into a regular air conditioner and heater, or would you have that completely separate? I mean, I think at the end you were saying, well, maybe you don't need it.
Yeah, exactly. So the whole idea is that the passive cooling capacity is that it may be like in a lot of climate zones, you could go through without using air conditioner and just basing it on this. But it's just like we have to do, and that's one of the things that we want to do is like look at what it looks like in different climates and different places.
But right now that's a commercial product, right? So when they're selling this and it's going into buildings, do the buildings also have active heating and cooling, or is this replacing it?
Usually it is, because it's usually going in, it is
what?
having an active cooling and heating device it pairs with.
Got it.
Because for the heating part, you realize that we can only preheat.
Right.
And the cooling part, we can cool a lot below and get passive cooling, but there's no way we could heat more than what we are getting inside in the room. So yes, so currently it goes in alongside a active cooling device, but it leads to lower size of that equipment, lower run times of that equipment it's getting paired with.
Right.
So there are benefits to it, but from a capital investment standpoint, in places where like heating is not dominant and it's mainly cooling, this product can substitute an air conditioner or a heat pump.
Got it. Thank you.
Sure.
Yeah, maybe you mentioned this already, but the condensate in there contains viruses and mold from the outside air. So how do you get rid of that in this system?
So the unit uses you're meaning the condensate coming out. So it goes through the drain, right? So that's
Yes, but it leaves also, the condensate comes out, but then it can leave those bacteria and mold growth inside the unit, which need to be cleaned somehow, or does
so usually, like from what I've heard, if it is because this water is getting drained, like if it is like you're using a recirculating pump to pump the same water back, then you're more worried about biological growth in the water. But if it is like once through water going through, you are just washing everything. And when you switch to the winter mode, what I call the HRV here, the unit goes through a drying cycle. So it doesn't leave the moisture still there. So it goes through a drying cycle where it blows the fan, this like, increases pressure and tries to dry it out. And you have to do it like once every year and, going back to drying cycle. And then when it wants to do it in the summer, it goes through a wetting cycle. So it uses some surfactant, like a little bit of soap, like a dishwashing soap, to wet the cycle, wet the unit out.
Okay.
Any questions online from our Zoom attendees? All right, well, with that, we will conclude our energy bites. Oh, wait, we have one more. Go for it.
So Subhrajit, with the exhaust that's going out, that's using evaporative cooling, right?
Yeah.
So there's moisture going out, which we use water to put into that. How much water is like evaporating out?
Yeah, I think, the better question to ask, I would be like, how much water do you like to have to put in, like, overall, like the input?
Okay, yeah.
Like, there's usually the two parts, it breaks into two parts. One gets evaporated out and one gets into the drain. So usually it is in the water, like it depends totally on the outdoor conditions. It's, and the unit, it has become a lot smarter. It usually has a solenoid and drips in water slowly, but you'll be within 1 gallon an hour. Like, it's like, I'm just giving you a rough number. It's less than 1 gallon an hour in most climates.
Cool, thanks.
Yeah. It's a good question.
Oh, let's see, we got another question here. Yeah, I guess someone's wondering if the Colorado module is a packaged product available in the US. Only source I think they looked online was from Sealy International Australia. So just wondering if it's how available it is and.
Yeah, it's available in the US and they are the company like Colorado. This is a lot before my time. They're based in Colorado, Denver. And so they are bought by Sealy International from Australia. And they're primarily like, it's a packaged product. They're trying to sell it to like commercial customers. But one of the things that we are wondering is that like, characterization of these units hasn't been done. And we are trying to get to the point where you can use this model that you have built, testing then the model and see where all it is applicable. And maybe with like people can start using those codes that I talk about in conjunction with like, use it as a modular thing to conjunction with the normal air conditioner.
Excellent. All right, well, let's thank Subhrajit, and we'll look forward to seeing you all on Zoom hopefully next week and in person. And those in person, we have some sandwiches for you.